Hi everyone. So in this video we'll finalize our discussion with hidden unit activation functions. So most of the video will be about the tanh function or the hyperbolic tangent function when used in hidden layer activation. So tanh is a variant of the sigmoid, meaning it's just the sigmoid with some transformations. Let's see how that works. So the sigmoid function, if you remember, this is used mainly as an output unit, right? And the reason it's used as an output unit is it has an exponential in it. So when used with cross entropy, the log undoes the exponential. So the sigmoid is typically used for two-class classification problems, and it operates on only one unit, which estimates the probability of the label being equal to one of the two possible values in two-class classification problems. Now let's take that function. So sigma of x, where x is an input variable, equal 1 over 1 plus e to the minus x. So this is a function that's bounded between 0 and 1. And it's active, or the variation is significant in only a small part of the domain of that function around the 0 point, right? So roughly from here up to here, the function changes significantly. Otherwise, it's not saturation, it's not completely flat, but very small changes around the function value of 1 and very small changes around the function value of 0. Now if I subtract half from this sigma of x, I get the same function but bounded from minus half to half instead of from 0 to 1. If I twice this value, so 2 sigma of x minus half, or 2 times sigma of x minus 1, then I'm basically doubling the value of the function, so it becomes from minus 1 to 1 instead of from minus half to half. Now the hyperbolic tangent is very similar to this function, but with compressing the x-axis. So instead of x, I have 2x. So this is basically compression. So it's the same as this function, but I'm squeezing it. So tanh is commonly used in certain neural networks which are recurrent neural networks. Let's see what's the reason as a hidden layer activation. Let's see what's the reason behind this. The main reason is that tanh of x is approximately equal to x for small values of x. And then it becomes bounded between minus 1 to 1. So in the active region, it's almost as the same as a line that goes from minus 1 to 1. And then it's it's almost saturates at 1, and in the negative region almost saturates at negative 1, right? So in the activation region, this function is almost a line from here to here. Now this is good for gradient-based learning because a line has a consistent gradient direction and a line doesn't saturate. And now the third thing which is important for recurrent neural networks is that the magnitude of the gradient is close to 1. Now the problem is, in recurrent neural networks, the same function is computed recursively multiple times, right? So now the gradient becomes the same gradient as you have in the standard feedforward networks raised to a certain power. Now, if that value or the magnitude is bigger than 1, then something called the exploding gradient happens. When you raise a value that's bigger than 1 to a large power, then it explodes. When you raise a value that's slightly smaller than 1 to a large power, then it vanishes. So it becomes, you have this phenomena with two-sided phenomena, vanishing gradient or exploding gradient. So now this happens in recurrent neural networks, and this is why using the hyperbolic tangent is good for these networks as hidden layer activation, because the magnitude of the gradient remains close to 1. Right? But the cost is that, of course, it has implicitly in it an exponential, right? It comes from the sigmoid, so it's more difficult to optimize than normal networks, and also because of the close to saturation regions, the almost flat regions here. So it's also, the training can be very slow when you are not in the active region, right? So that's why usually recurrent neural networks take more time to train, right? Because they use the hyperbolic tangent as a hidden layer activation. Now the second type of activation functions that we want to discuss before finalizing the discussion of hidden layer activations is what's called linear activation. Now, if you remember the XOR example and the motivation of depth, we said that if you have a series of linear functions, then there is no need to have this series, right? Because you could squeeze them into just one layer, right? And that's why activation functions rely on nonlinear functions, because otherwise you wouldn't need them, right? So what's called linear activation is actually not really an activation function as much as it's a transformation in the network to a lower dimensional subspace. So what happens is what's called linear activation refers to having a hidden layer with a smaller dimensionality than the two layers around it. So let's say, for example, I have an input layer with 6 neurons, an output layer with 10 neurons, and I have a fully connected network, then this is 60 weight parameters. Now, if instead I have a hidden layer with 2 neurons, so I compress the 6 neuron input layer into 2 neurons, and then I go back to 10 neurons, then here I will have 12 weight parameters, and here I will have 20 weight parameters. If I sum them up, then I have 32 weight parameters. So I'm effectively, when I add this bottleneck layer, right, I'm effectively reducing the number of parameters, or more specifically, I'm reducing the complexity of the hypothesis space, right, that I'm using for learning. Now, is this good or bad? All the arguments that we had so far about the complexity of hypothesis space applies here. So it can be a good thing to reduce the complexity for generalization, for example, and it can be a bad thing and causes underfitting. Now, typically, I would use this if I believe that all the information in the 6-dimensional subspace should actually be compressed into a 2-dimensional subspace. So basically, the important information can be represented into a 2-dimensional subspace. If that hypothesis is correct, then this would be a very useful thing, because it would get rid of all the noise in the bigger subspace. Sounds good? Now the last thing is what we discussed before, the radial basis function kernels, which is basically having a center point, and then for every point x, the value becomes a negative exponential. That's a function of the distance between x and the center point xc. Now this is a very representative function when used as a nonlinear activation, but it has its problems, right? So as we discussed before, it's a very complex function. So that means its training or its optimizing it is a very non-trivial thing. And also with gradient-based learning, this is not encouraged at all, because there is gradient saturation due to having an exponential. So far from the center point, the value of the exponential almost flattens out. So gradient-based learning becomes very difficult. And also in the active region, you have inconsistent gradient direction, right? Because the exponential changes very quickly, so the gradient direction can change as well. Thank you.